Ian Green is a recent graduate, having completed a BS in Computer Science and Mathematics in May. Prior to studying computer science, he studied mechanical engineering, chemistry, and anthropology. Ian has spent most of his life working as a chef and holds an Associates of Applied Science in Culinary Arts. Intermixed into this long list of educational pursuits and cooking have been stints spent as a machinist and community administrator of a large student organization. As most days and nights have been spent working to afford the bills for university, Ian has found many of his technical and academic interests relegated to the stuff of hobby. Over the previous decade, many of these interests became woven together by means of keeping crabs and other exotic pets. As a person who is both blissfully lazy as well as cheap, this combination of hobbies and education have resulted in a lot of development and fabrication work to automate as many aspects of his pet-keeping responsibilities as possible. Please welcome Ian Green.
Ian Green. This presentation is Do-It-Yourself Environmental Control Systems, a homebrew technical solutions for exotic pet care. The first thing I have to do is read this disclaimer to you. You can tell it's important because I put it in red. I'm a computer scientist, not an electrician or an electrical engineer. While I personally am comfortable operating the devices included in this presentation 24 hours a day in my home, it must be emphasized that these are demonstration units. Many of these projects involve some degree of safety risk due to their electrical nature. This risk is entirely manageable and can be minimized by studying both basic theory as well as regulatory manuals. For permanent installations, I strongly advise studying best practices for at-home electrical projects. Getting involved in a local hackerspace or joining an online community such as the Arduino forums is a great place to start learning from experienced professionals as well as like-minded hobbyists. So the problem that this presentation is aiming to address, whether it's due to inadequate technology for managing tank environmental factors or the inability to afford existing solutions, many exotic pet keepers find that long-term management of their tank's environment becomes either a hassle or impossible altogether. Many people in the community are either using a basic Petco thermostat or they're using low output heaters, which they've just passively tuned to stay around the correct temperature with no actual controlling of the heating elements. While they're both valid setups, a fairly small amount of elective learning makes it possible for us to provide better control as well as increased safety. As with many things, particularly in this hobby, cost is usually the deciding factor when selecting what hardware to use for tank management. High-end or custom solutions for exotic pet enclosures are usually targeted towards pet keepers with extremely deep pockets and are kind of out of the reach of most of us. This market paradigm can be subverted fairly easily due to the fact that most, if not all, control components can be purchased cheaply online and fit together like Legos. The amount of learning and effort required to build your own control system ranges from trivial to substantial depending on how complex or unique of a solution you desire. So the three main areas I'm going to cover are reviewing some basic store-bought packages that a lot of us will be familiar with, a fairly detailed but quick review of introductory do-it-yourself systems, hybrid. I sometimes get called Lego systems because you can just kind of piece them together, click them together, and they typically work. And then finally, I'll do a very high-level introduction to complete custom control systems. My goal with that is to get you interested in it, to basically advertise and convince you to pick up a new hobby related to computer science that involves your pets. But I will not be going into quite that much detail with it because it really is a large thing you have to learn. It's a whole hobby you have to adopt. So beginning the review of the off-the-shelf components, many of you are probably familiar with, if not this exact unit, one that looks almost just like it. This is the most common type of thermostat that I believe members use, and it's the most common one to encounter in the store. This type of unit, fairly basic, displays the temperature, displays the set temperature, and it holds the temperature through its one output. It's fairly limited though. It only has one temperature sensor. It has one relay, one switch, so it can only control off and on for one output, which can be multiple heaters if you have them on a power strip, but it's one element of control. And typically, this isn't always the case, but typically they don't have any overtemp or failure mode alerts, warnings, alarms, anything like that. They're pretty cheap though. Not if you buy them in a pet store. They'll still try to get you for about $50 or $60, but online, usually somewhere around $20. There is an issue with this and with pretty much every single piece of hardware I will mention in this presentation, and that's that you can't always trust in that you paying more for a product necessarily guarantees that you're getting more reliable hardware or a better engineered product. Sometimes it really is just 5 versions of the exact same cheap product with a fancier sticker on the ones that cost twice as much. That's true for everything. You can really only combat that by personal experience, learning which ones actually are better and which ones aren't. This is, let's call it middle of the road off-the-shelf unit. It integrates a timer controller, you get a fancier display, but you still only have this one temperature sensor and you still only have one temperature output. This is perfectly sufficient for many tanks, particularly if you're using a higher end, more self-contained heating unit. It has pretty much the same capabilities, but the additional light timer capabilities, and it has pretty much the same limitations. You have your slightly fancier ones. We don't typically see these in stores, but they're quite available online. Units like this, you usually have more than one temperature sensor and you have more than one output. But a limitation that I see with these is that while there are 2 outputs and 2 sensors, they're not related to each other. They're 2 completely different systems for controlling 2, either different tanks or different outputs. They can't inform each other. And they do tend to get fairly expensive. I doubt many of us use a system such as this as the Herpstat 2. These are fairly common in high-end reptile keeping, but they can also be used for, hermit crabs. There's a lot of systems like this brand. These are basically someone who took the last segment of this presentation about advanced control systems and commercialized that product. So these can be incredibly complicated. It might take you a week or 2 to learn everything that's actually going on inside of it. A lot of them have advanced timers, advanced heating responses. This one in particular is passcode. If you have to worry about kids or something, there's passwords to get into it. You can do advanced lighting. So if you want, your morning, when your lights come on in the morning, if you want them to cycle on slowly, so you have like a sunrise and a sunset, you can do that kind of complicated stuff. Some of them have humidity management and control or notifications. There's a lot of possibilities that come out of these type of units. However, they are generally extremely expensive. Some of them, particularly high-end aquarium management systems, I've seen for well over $1,500. These reptile ones seem to be a bit cheaper, but there is still a problem with this, in that because our hobby, hermit crab keeping, is an atypical tank setup, even if you spend a lot of money, you might still not get the exact set of features you need to minimize effort and maximize safety and maximize your possible laziness in not having to worry about a conditions failure in your tank. So we have what I've called Lego systems, our hybrid systems. I'm going to cover 3 of these: the basic thermostat, the basic safety thermostat, and multi-factor controllers. The secondary load handling, something we'll talk about later. You can very cheaply get these just basic industrial or commercial temperature control units off Amazon or eBay or wherever on the internet. The individual quality of each unit sometimes has to do with how much you spend on them. Sometimes it doesn't have to do with how much you spend on them. That's, again, really just an experiential thing. So for our absolute basic, this unit, I believe I paid $15 for the example I bought. It manages heating and cooling. The cooling's not really that relevant for most basic setups. If you plan, first off, it's not generally a problem that, due to the heat capacity of your tank, it's unlikely that it will ever actually overheat to such a degree that you would need active cooling. I do run active cooling on mine, but that's for kind of more complex reasons. But even, this $15 unit, you're already looking at a third of the cost of the basic off-the-shelf Petco controller. It handles heating and cooling cycles. You can do some tricky stuff with the cooling cycles if you want to. Let's say you want a light bulb above your crab tanks to turn on and let you know when it's too hot. Maybe you need to pay attention to it and track it over time or something, or you just think it'd be interesting. Well, you can wire just a light bulb, a labeled light bulb or something, to your cooling side cycle of this thermostat controller, and it doesn't actually have to cool. You can use it just for notifications, or just not use it at all, like we won't in this example. So I know this may be a bit tedious, but I am going to play a video of start to finish building one of these systems and talking about it a little bit. So this is our simplest and cheapest example of a basic off-the-shelf component thermostat. We will be following most of the diagram on the back here. we won't be concerning ourselves with the cooling circuit, since the vast majority of people won't be using cooling fans because it introduces humidity problems. First, we remove the protective terminal cover. Which allows access to these wire terminals across the back. I'm going to use these two cables. I would suggest buying a extension cord of whatever length you need and cutting it in half. I just happen to have these two already chopped cables at hand. So after stripping them, the wires, and clean them up a little bit, so we want to have the load, the black wire, as the one which is being switched by the relays in this. So we'll be wiring neutral to 1, load to 2. Neutral in 1, load in 2. And we'll be undoing these terminals multiple times, so don't tighten them down all the way at first. And our output end, we're going to want to tie its neutral white line directly with the other one in terminal 1. If you are going to use this as a permanent installation, it might be advisable to solder these together so it's a little bit more stable. But we'll talk about that a little bit more later. So we have both neutrals on 1, load from the wall on 2. We need to bridge terminal 2 to terminal 5. 5 is the power input for our switch. Five and 2. 5 and 2. When you're sticking multi-strand wires into these terminals, you always want to double check that you don't have any stray little hairs sticking out to the side. And make sure you get them all inside the actual terminal, which I did not do with the second neutral wire. So I'm going to redo that now before I forget. So at this point, we have both the input and output power cord neutrals in 1. We have the input load wire in 2. And then using this extra wire, we've gone from 2 to 5. 5 is the power in for the switch, and then 6 is the power out. So that's the terminal that will be sending the power to the heating element. So we'll wire the black, the load wire of our output cable into 6. And I'm going to redo the neutral one because I still don't like how it turned out. You need to make sure that you leave enough space with all these wires so that they're not strained, they're not tugging on each other themselves. And then this unit comes with this little sensor wire bundle. The sensor wires don't have a specific polarity. It doesn't matter which way you wire them into their terminal blocks on 3 and 4. So we're just going to put those in real quick. You're going to be fairly gentle with these terminals and with this board. You don't want to screw the terminals down real hard. You don't want to yank on it too hard. They're pretty, I don't want to say fragile, but they're not robust. Let's say that. So we have both of our neutral white wires in 1, the load wire from the wall in 2. 2 is bridged to 5. 6 goes to the load of our plug end. And then the neutral for this plug end is the second neutral wire we put on terminal 1. At this point, this unit is fully wired. For demonstration purposes, I'm going to be using this light bulb instead of a heating pad because you can't see a heating pad turning on and off. So we connect that to our output cable, and I will plug it in. So these specific units contain non-volatile memory, so they won't forget what you do when you turn them off, which is very nice. So this one is probably pre-programmed. For this specific unit, the guide is actually pretty good. Some of them are awful. Some of them have completely wrong information in them. But Inkbird's kind of middle of the row. It's all right. Their guides are usually okay. So we're gonna cycle through the settings real quick. And basically need this book to decipher what this says. It says TS, temperature set value. I have it on 81. DS is difference set value. This is how many degrees have to change beyond the set value for it to actually do something about it. I have it at 2 degrees. Let's put it at 1. This is more a concern if you're heating and cooling, but basically if you don't want it switching on and off for every single little thing, you would increase that delta value. There's CF in the settings. You can set Celsius and Fahrenheit. PT setting is irrelevant for us. That's for like a refrigerator application. CA is also largely relevant for us. So this is basically configured. It's set to 82 degrees with a 1 degree difference. So right now it is 78.7. I have some hot and cold water over here to use for demonstration purposes. These are cold and are hot. So right now, I'm going to put it in the cold to cool it off. So right now, the heat light is indicating, and the light bulb is on. So your heating pad would be running. Hopefully it never gets this cold, because it's very cold. So I'm going to put it in the hot water now. And as it climbs back up, it will cross our set temperature value, and it will disable. Now it's gone into cooling mode. We don't have anything wired to the cooling switch, so it's basically doing nothing. So I'm going to pull it back out of the hot water. But as you can see, the light bulb turned off, so your heating pad would be off. I'm going to put it back in the cold, cool it back down. And now it's heating again. This is the most basic configuration for this unit. This is the same as the most basic off-the-shelf units, thermostat units that they sell at Petco. These particular units are capable of handling 10 amps of output. They're able to switch a 10 amp load. That's far beyond what any of us are likely to ever use, especially for a configuration like this, so it's safe. Later we'll talk about what you do if that's not quite enough, a little bit more involved. But this is sufficient for running most typical small, medium-sized pet tanks. This configuration of wiring it's good for demonstration purposes. It's not great for long-term use. So ideally you'd want to get a box, a plastic box, metal box, cut a hole the size of the body, the dimensions of the body, but smaller than this faceplate. You just slide it in the hole. You slide these little plastic clippies up the side, and it pinches it into the front of the box. Ideally, you'd also want to zip tie or wire tie your cables to the inside of that box, or at least to something secure, so that if either of the power cords or the sensor gets tugged on, it doesn't tug directly on these terminals, it just tugs on what they're attached to. It's called strain relief. It is a very good idea to do. And in about 5 minutes, you have a basic but functional thermostat unit that you have a little bit more freedom with. You can fine tune it a little bit better. You're more free with what you have plugged into it, and it's only about $15. All right. So, a summary of that. It's pretty basic wiring. You don't really have to learn too much. Maybe suggest reviewing a code book or regulatory manual on the subject of what's considered safe and not with wiring. But it's cheap. It's mostly sufficient, and it's expandable. If you want to add to it, change it, remove it later, it's fine. Not going to be a problem. Next up, we have kind of this, what I've called a basic safety hybrid system. This is 2 of the exact same unit we covered in the last segment in that video. The exact same capabilities, limitations. However, this configuration is a little bit different. I prefer this configuration with most of the controllers, even if it's not using these little controller units. The same style of system is generally what I look for to consider something safe. And I'll talk about that in the next moderately tedious video that I'm going to play. If you didn't know, we're playing a game where you count every time I say for demonstration purposes only. There is a fairly substantial safety risk in my mind with some heaters. This doesn't apply to all of them, but if you have the type of thin film heater that gets exceptionally hot when just plugged in, we have a problem that's often overlooked or isn't addressed. If you have one temperature probe and you're trying to control the temperature of your tank, you're going to set it at about 80. Well, that thin film heater, flex tape, flex watt, underfloor heater, whatever you want to call it, and some of the other mat type ones, they're going to get very hot. They don't all do this again. It depends on the wattage per square foot, but some of them can get upwards of 200 degrees. It's a safety hazard. They're more likely to fail, and also it's not ideal to have the back wall of your tank sitting at 140 degrees on the outside or 110 degrees on the inside. So this is you won't pretty much ever see this functionality in a normal off-the-shelf pet controller product. But what we're going to do is we're going to take two of these basic $15 units, we're going to combine them, and we will get control for the maximum temperature of the actual heat mat and control for the tank temperature. It's pretty simple. It's not that different from the previous one. I have unplugged the power from the wall. The output is still plugged into the light bulb. We'll get to that eventually. So this one's a little bit more complicated, but it's really not much more. I'm going to disconnect all of the wires that we attached in the previous example. We will still not be using the cooling relay, the cooling circuitry involved. So here's our one sensor, and here's our second sensor. So we have our two units. So both units need power. They both need load and neutral. But what we're going to do is we're going to use, instead of having the power directly go from the switch output to the heater, we're going to have it go from terminal 6, the switched power. We're going to have that run into the power source of the second unit, so that when, let's say this one is set to your 80 degrees, this is your tank unit. When it is under 80 degrees and it wants to run the heat, it's going to close the switch and power will start flowing to your output. But it's going to go into the power source for the switch on the second unit, and this one will be our actual heating element unit, and its temperature probe will be attached directly to the heating element on the outside of the tank. And so what this is less than 80 degrees, it wants to run the heater, it supplies the power to this one. This one, let's say it is ambient, it's been off, it's also, like 75 degrees, so it will be in heating mode. It will run until the sensor probe on this unit hits whatever we set, whatever we feel safe, and then it will cut the power here. And the heating unit will turn off, it'll cool down, and then it will re-engage, and it'll turn it back on. This allows us to have one monitoring tank temperature and driving on or off to hit that target temperature. And then this one will be switching more often, off and on, to moderate the temperature of the back wall of the tank and the temperature of the heating element itself. So we're going to need a couple extra wires for this one. Some of this stuff might be wise to do, to solder these connections if they're going to be permanent, depending on your skills or tools. These little things are fine since it's going to be in a fairly protected environment. So we're just breaking out the neutral and load from our wall source into two so that we can power both of these thermostats. Make sure they're attached strongly. This is, for any kind of large heater or one of these hot heaters, this is really what I would consider to be the minimum safe temperature controller. But again, if you have a heater that never gets over 95 degrees, one of the low output, low watt per square foot units, then it's not really as much of a concern. But I've seen some horror stories relating to burnt up heat tape so I like this. So first, tank and heating element. Going to attach our tank controller first. And our sensor on terminal 3 and 4. And like before, we're going to bridge our load, our terminal 2, to terminal 5 to provide power for the input side of the switch. But unlike before, instead of going out from terminal 6 to our output socket, we will be going up to the power input for the switch on the second unit on terminal 5. So we put that in 6 and into 5. Go ahead and attach our second temperature sensor to terminals 3 and 4. Again, the direction doesn't matter with this type of sensor probe. And then we will attach our neutral and load to this unit as well. Always making sure that we're not popping them out of the first unit we put them in. We'll attach our black load wire going to our output plug to terminal 6. And the neutral back to terminal 1. They all share the same neutral here. It's just convenient. Always checking to make sure that you don't have frayed little wire ends from this annoying multi-strand wire. Make sure they're all tight. Okay, so we'll just check our brains real quick. Neutral comes from the wall into 1 on each unit. Neutral from our output is also tied into 1, which connects it to the wall. Load goes into 2 on each unit. Load on the bottom unit goes from 2 to 5. And then the output from that bottom unit goes from 6 to 5. And then 6 on the second unit goes to our power output. And that's it. So I'm going to zip tie these together real quick for demonstration purposes. So that they don't fall apart as I play around with them. Like I said in the previous example, you really probably want to secure these inside of a box, project box, to the tank stand, something safe, especially if you have kids or pets. I don't really have to worry about that in this particular example. To unbundle this second sensor. And we should be all set to test. Okay. I'm going to temporarily unplug this heat source until we have these both set up. So Bottom one, I have the probe and the cool. So the bottom one will be our tank. Let's check to make sure it's still, that I got them right, but it's the one from before. So temperature set, 81. So this is the tank controller in this case. We'll go back. So it's already set up from the last example. Let's go into this one. Temperature set, 82. So this is going to be our heating element. So what temperature you feel safe with is up to you. It's a 50-watt light bulb. I'm going to just, for demonstration purposes, set it at 100 degrees. So it's at 100. We'll give this a little bit more flexibility. We'll give it 2 degrees of sensitivity. Irrelevant, irrelevant. Already set to Fahrenheit, so we're done. Okay. So I'm going to plug the light bulb back in, which is our stand-in for our heating element. And I have the sensor hooked up here. See how long the temperature takes to go up. So I have the tank probe in cold water, so it wants to heat. So it's driving the heater. And right now, the heating element sensor is only about 90 degrees, so it's also heating. So there's power flowing through both systems to the heat output. Now the temperature's starting to jump up a little bit quicker. Once it hits 100, 101, we should see it switch. So it just turned off, and so did our heat source. Now this tank controller, and it went into cooling mode, it's irrelevant because we don't have it wired up. Our tank is still trying to drive the temperature up because the light bulb is turned off, but the first one doesn't know that. That's okay, doesn't matter. So I'm going to accelerate this a little bit. We'll cool this probe off. We'll pretend it's been a little bit longer since the heater was on and it came back on. Now we'll heat up the tank probe, get it turned on. So our temperature's rising because the light bulb's on. This is just like an accelerated version of how it would be with a tank. Our tank temperature is rising. Now the tank's off. Now you can see this one, the heating element one, still wants to run because it hasn't hit that upper threshold yet. But because the tank controller has already cut the power, it doesn't have the ability to drive that heater. And we'll cool it back down real quick because why not? So now the tank is below 80. It wants to heat again. This is less than 90, so it's heating. So my water's cooled down quite a bit. So still, again, the tank is heating. It wants to heat. The probe for the heating element is below the threshold, so it is driving the heating element and crossed over. Now the heating element's off. So what this configuration allows us to do, like I said before, is it allows us to control so that this heating element, in this case a light bulb, but in reality your possibly dangerous high output flex watt heat tape, can never really hit its maximum temperature. You could buy some underfloor heating panels or something that, have a natural maximum temperature of 90 degrees, 95 degrees, if I remember. But a lot of the stuff does tend to be on the high output side, especially if you're talking about that 4 or 6 inch tape. This doesn't have like redundant fail safes in it. It's not going to detect a short condition or any of the other possible failure modes for those thin film heaters, but it does allow us more fine control and quite a bit more safety than just running the one thermostat. And the off-the-shelf pet store controllers with the one sensor probe, they don't take this kind of stuff into account. They assume you're going to use a certain product with them, or there'll be a line on the back that says no safety guaranteed unless using this exact heating unit that you buy from us. This is my preferred style of setup. The alternative to this, and I've told people in the group to this before, is if you do have, like our previous example with just the one thermostat, it's actually better to put your sensor probe on the back wall. And you have to kind of do this dead reckoning guesstimation game of how high can I set the thermostat so that the tank still gets the temperature correct, at the actual tank temperature reading is correct, but the thermostat's able to switch your heater on and off, and you have to kind of extract from testing and trial and error. You have to extrapolate this zone of safety where your thermostat might be set at 98 degrees because in testing you find that if it's turning the heater on and off at 98 degrees, it's actually able to keep your tank around 80. And that's safer than just running the one thermostat inside with the heating element on full blast.
but it's kind of tricky and vague and not great. So these two $14, $15 units, $30 with an extension cord or some scrap. Uh, project box, that can be free if you have some piece of junk you can cut into, or a thick wall Tupperware container or whatever, or a legitimate project box from an electronics website, or conduit box from Home Depot or something. This provides us quite a degree of increased safety.
Okay, so hopefully that wasn't too tedious for you. Uh, so as with the first example, the wiring's still basic. Still don't have to do a lot of research. It's still pretty cheap, looking at about $30. Sufficient for most setups, and like before, it's expandable. You can add to it. You can change stuff later. We didn't use the cooling relay on either of these units in either example. There are creative solutions you can do with that actually do relate to cooling or other things like I mentioned before. If you noticed in those videos that after these units enter cooling mode, the lights stayed on, which seem a little anomalous. That's because these units use mechanical relays, and I don't have any load present across the cooling circuit switch. So once it turns on, it latches on. It doesn't turn off. It doesn't matter in this particular example because there's nothing connected to it. It's not actually doing anything. But in more complicated systems, you just put a load across that. That relay doesn't latch. We'll talk about relays a little bit more later. I'm not a huge fan of mechanical ones, but they're cheap and they come in a lot of stuff. All right, so multi-factor controllers. You can also get these, off-the-shelf component level units that will read for and control temperature and humidity, and you can kind of hack that into controlling other things if you want. There's hygrostats on this. You can do something based off that humidity level if you want to do something similar to what we did in the last couple examples, but let's say maybe you don't want to actually deal with the humidity because that gets kind of tricky. You don't want to add and remove it or refresh the air or anything like that. You can just, like I said before, hook up a light to it, and that way maybe you have a warning system if your humidity is out of whack, and it's also just convenient to have the readout there. These units, I don't really want to make this about these exact specific Inkbird units because I really just chose them at random. There's different qualities of them. There's different costs of them, obviously. Different feature sets. The thermostat used in the first two examples can do Celsius and Fahrenheit. This one only does Celsius. That doesn't bother me. Maybe it bothers you, so you look for a different chipset, a different unit with different capabilities. There's almost an endless array of these units. You can tie them together to make more complex behavior, more complex control systems, but I wanted to show you those start to finish videos because just to reinforce how absolutely quick and easy it can be to get a control solution that just simply doesn't exist in most off-the-shelf controllers. That, like I said in the video, you're never going to find a thermostat unit for a pet tank that takes into consideration the temperature of the heating element as well as the tank set temp goal. I think that's a severely lacking feature. It's pretty important. So with these multi-factor controllers, again, still pretty basic. That one actually, the one pictured here, has fewer wires and fewer stuff to do than the previous one. Than just the thermostats. It comes with a humidity sensor, little bundle thing already attached to it. They're cheap, again, sufficient and expandable. There's a lot of these different multi-factor control units that you can kind of piece together. Pictured here is a PID controller. This probably isn't as important for us with our pet tanks because they have such a large thermal mass. They have such a buffer zone between the temperature output of the heating elements and what is actually reflected in the conditions in the tank. But say you wanted to maximize it for energy efficiency, or you don't want to be switching the elements on and off all the time, you can use these PID controllers. They use some complicated calculus internally. You got to learn a little bit to learn how to program these, but to be honest, most of them come with an auto-tune feature, so you can actually get away without learning very much, without having to study very much anyway. They use a little bit different approach. It doesn't just click on and off. It learns. It uses sensing and memory to determine, okay, this is what happens when I turn it on. This is what happens when it comes off. So maybe next time I do this a little bit differently, and it fine-tunes itself down to where it can predict the rise and fall and run the heaters more efficiently. Those are very good for some particular applications, probably fairly unnecessary for a basic heating system. So this is the part of this presentation that I'm most passionate about, and I'm going to handle a little bit differently. Custom control systems. In order to get into this, you or your child need to have an interest in, some basic programming, electronics. There's a lot of different solutions for this, a lot of different platforms to work with. Arduino is what I'm going to cover most heavily here. You can also do it with a Raspberry Pi. It's a little bit more higher level software driven, a little bit less friendly for these analog sensors and input output sensor bundles and controls, but it can definitely be done with those too if you're maybe a little more skilled in that area. There's a whole industry that exists related around making it easy for you to do complicated electronic tasks. There's essentially no limit to the potential of what you can do with these systems. It's very easy to start, particularly with the Arduino, it's very easy to start out. There's a huge community of people who are themselves just learning, who have no experience with programming or electronics, who want to help you learn, who aren't going to be mean to you or judgmental or presumptive or any of these other things we're also used to finding on the internet. This is a great way to get into really anything you can creatively think of in your head. You can pretty much build with an Arduino or another one of these testbed platforms. And once you do it once, you can kind of, there's some degree of future proof involved with this because you can always change it, you can always update it. I still use the original Arduino to control my main tank that I started using probably 8 years ago. There's been probably 60 different programs run on it to account for different tank setups and conditions and hardware and equipment and stuff, but it's still that original Arduino. It's been running 24/7 for close to 8 years at this point. All right, so from here, I'm not going to mention the Raspberry Pi and stuff again because it's a little bit, if you want to make some beautiful solution with a beautiful display output and user interface, that's great. Do it with the Raspberry Pi. It'll look pretty. If you're just starting out, this Arduino is probably the way you're going to go, and it has the largest community surrounding it. It has the largest availability of sensors and parts and all these little bundles and stuff. So it's cheap. This unit, $20 to $30, usually $25. You can get them for $5 if you have the equipment and the desire to solder all the components onto the board and stuff yourself. You don't want to just buy a pre-bundled, pre-manufactured unit. You can get them extremely cheap. You can get them even smaller if you want to embed it in your tank structure or something in a aesthetically pleasing way. There's just limitless options for this stuff. If you want to start out with a focus on learning coding and use this kind of as your vehicle to do that, you can start with the component level, the electrical components. You can build all your own circuits. You can program it from the ground up. That's great. I love that. I encourage that. However, they also know who their customers are. You can buy complete pre-bundled, pre-manufactured, they call them shields with Arduinos, but basically sensor add-ons. A lot of times they come with pre-existing code, and you can just kind of drag and drop your parts onto the Arduino, and you can drag and drop your code into your programming environment, upload it to the Arduino, and 85% of the time it just works. And maybe you have to tweak it a little bit. Maybe you have to go on the Arduino community or whatever and talk to someone, get them to help you through getting it to actually run, do a little research. It's a generally pretty enjoyable experience, not too complicated. These development boards make it very easy to get started with this. It's not as daunting of a task as sitting down with a pile of discrete electrical components and having no idea what to do. And like I said before, there's tons of people who would love to help you with this, with whatever your project is. Because relays will be involved with most Arduino projects, I'll go ahead and talk about them right now. With those previous thermostat self-contained units that we used in the hybrid examples, like I mentioned, they have a 10 amp capacity. The Arduinos operate on 3.3 or 5 volts, and you're unlikely to be switching, trying to control appliances that run on 5 volts DC. They're almost all going to run on 120 volts AC. So you use these relays. If you don't know what they are, basically you have, let's see, with this particular one, you have on the right side 2 terminals and on the left side 2 terminals. Well, you run your load wire from your AC 120 volt through these 2 terminals, and you run a control wire from your Arduino through the 2 on the right. Or you can actually kind of multiplex this with those off-the-shelf thermostat units and get some pretty complicated behavior out of them without ever having to program anything. But these basically just allow you to switch a low voltage on one side and control a higher voltage on the other side. Very important. They're the likely thing to fail in one of these systems. If you're going to have a catastrophic failure, either in your own hand-built system, program system, or with one of those hybrid thermostat units, it's probably going to be the relay that fails. It can be kind of dangerous when they fail, depending on how they fail. They have a tendency to fail on, which is not ideal. You can, of course, develop solutions around that to prevent that from happening, or to sense when it does happen and kill power to the whole system, which is advisable. But quality is a concern with these. There's a lot of counterfeit ones. I actually have a really hard time buying legitimate ones offline at this point without buying them from a mega conglomerate electronics component supplier. DigiKey's a safe buy. They're not likely to find bad counterfeits on there. Amazon, lots of counterfeits, but that's not always a problem, especially if you're handling low loads. I think the risk of failure kind of increases with with your expectations for the unit, for the component. This particular one pictured here is, you could run a oven off of it. It's way overbuilt for anything we're talking about here, but that's why it has a heat sink. It kind of generates a lot of excess heat while working. But these will be integral to basically any system you build or you think about building. You can switch pretty much any appliance with these as long as it doesn't have some kind of boot up loading screen system. It might get a little confused with that, but they become very important. All right, so in this world of Arduino sensors and components and projects, what are some things we might want to do relating to crab tank control? Well, heat, humidity are the obvious ones. Maybe we want the moisture level of the substrate. Maybe we want to put 3, 4, 5 moisture level sensors in there so we can kind of generate a map either in our heads or in a spreadsheet, or you can graph it if you care to. You can, code a output that has a constant live graph of this stuff, of all this stuff, if you want to. It just takes a little bit more research and a little bit more effort coding. Maybe you just put some moisture sensors in the bottom of the substrate against the bottom glass or the bottom of the side glass. That way you have a flood detection system if you set it up to only trigger after a particularly high moisture level. Maybe you want water level sensors in your tanks and your water pools, or a float sensor so you can set like a warning at a minimum level if you have a hard time remembering to replace the water or fill the water if you have a persistent water tank, like a small fish tank. You can control your lighting schedule. That's pretty easy. You can do really complicated things. That one, the high-end off-the-shelf system, that herps that too. Like I mentioned, it does the whole sunrise, sunset thing. Well, you can do that. You can do it very complicated. You can do it as complicated as you want. You can mix in different colors that turn on at different times as it cycles through. If you have a real-time clock integrated into your Arduino, maybe you want to give yourself, based on a random number generator, a 25% chance that any given day there might be a storm, and you want to do something where you turn off the brightest lights and maybe turn on some grayer or bluer lights, or simulate some kind of complex behavior, lightning, whatever you want. You can do, like I've said, probably an annoying amount of times at this point, anything you want. There's pH sensors, salinity sensors, total dissolved solid sensors, electroconductivity sensors. Let's say you wanted to integrate some fish tanks, partial fish tanks, whatever you want to call them, more complicated water pools, but you either don't trust yourself or you're just interested in the data, you want to automate that. Well, you can integrate enough sensors into one of these Arduino systems to monitor water conditions. Maybe even if you get really involved, you add some sump control and water addition, and you can automate the adjustment of pH, salinity levels, water levels. That gets a little bit more tricky because fluid dynamics is scary, but those systems, you got to add a little more checks in them, a little more redundancy systems, because you don't want to flood your tank or whatever. But it's definitely feasible, and you don't have to learn every single little bit. This image I have over here is pulled off a manufacturer's website. It's just a system you can buy for pH, if I remember correctly. Maybe you have a kid that has a habit of getting in your crab tank or pets or something. You want to embed some micro switches along the lid line so there's lights or warning sounds that go off when the lid's opened, or maybe you want to data log that to see if some long-term temperature or humidity behavior has something to do with your periodic opening and closing of the lids. You can do that. Air pressure, a little bit hard to see how that would fit into this, but it's definitely available. And let's say you want to make a redundant fail-safe notification system for your pool bubblers or something like that. Definitely have those sensors available too. I'm going to hop out of this presentation real quick and show you guys in a little bit more detail what's available. One of the great things with this Arduino community is that people aren't usually too cagey about their projects. It's very common that you can just find a completely built project that will very closely fit your needs. Like, really, what's the difference between an autonomous indoor greenhouse and a crab tank? It's really not that different. If you don't know where to start, you find one of these projects on the Arduino Project Hub or somewhere else, and well, look at this. It tells you all the parts you have to buy, and conveniently, it has product links where you can go buy them. But it's not really important. What tools you need, and he talks you through building it and how it went together, and this crazy rat's nest that should probably be cleaned up at some point in the future. and the mechanical systems, because in this particular example, they're controlling water flow. So this would be kind of related to that whole automatic fish tank management thing I mentioned earlier. The moisture sensors, irrigation, you know, all this example for all these different things you can do with the parts required to do it. And look at this, here's the software to run it, a working version of the software. So you can look at this, decipher what the solution they use code-wise to get what functionality they have, and it's really helpful to have a place to start from with code projects like this, especially if you're new to programming. And a lot of times the people on this website will talk to you about their projects and help you diagnose issues you're having. Maybe you want to have like a hub. You want to run a little web server on an extra computer in the house or something. So when you're at work or when you're at home, you can check a bunch of readouts from your tank conditions. I do something a little bit like that, but I've limited it in recent years because it's not really that important to me because I've come to trust the automatic management of the system. But here's a real simple relay humidifier appliance. Power. This is a lot like what we were doing with the thermostat, except you can program it yourself, and there's lots of help here for it. Weather station, again, is crab tank management really that different from a weather station? Not really. So you can take some bits from this, this code that's generating these nice little graphs. Maybe you want that. Maybe you want to output that to a file somewhere and save it so you can look at it over time and maybe draw some borderline scientific conclusions from your gathered data. Very helpful to have these projects to go off of. So just to emphasize to you how many different discrete components are just sitting out there ready to be hooked up to an Arduino, there's a lot of these websites that kind of specialize in non-expert hobbyists. So you got liquid levels, flow controllers, flow sensors, volumetric flow meters. This is just for water stuff, but lots and lots of stuff. Here is the pH and salinity one that I mentioned earlier. This particular unit is not cheap, but pH and salinity sensors, even if you're just buying them off the shelf aren't going to be cheap anyway. It's a little bit more of an advanced functionality and type of sensor. But here it is. Here's the stuff you got to buy. Here's them talking about how you use it, identifying each wire. It's a great way to learn how to do this stuff, especially when there's a version that works. And then with a sensor like this, they have libraries that you can import that run that kind of offload most of the responsibility of coding from you to them. And code examples of how to do it. You start with something, one of their examples, it works. You change it until you get to what you want. It's great. It's a great way to do it. It's a lot less frustrating. Arduino in particular is particularly known for these things called shields, which are just like kind of semi-self-contained little units, sensor units typically, or driver units that contain everything. You don't have to mess with the individual components. You can just trust that it works and integrate them into your system. And again, lots of examples, how to do it, how to read it, how to wire it, how to program it. So it definitely makes it a lot less daunting. Speaking of that moisture sensor, you might be familiar with the classic two-prong sensors that go into pots or whatever that have a tendency to work for about 2 weeks and corrode. Well, here's a capacitive one. It doesn't have that same corrosion issue. It's $750. It's pretty cheap. They suggest you buy wires with it because it has this convenient little organized pinout wiring harness thing. So let's say we buy this for $750, and the little wire that goes to it's $1.50. So we're looking at $9. Well, it's really clean. It's really convenient. It just plugs in. The product, Adafruit, this particular company, has a guide like this for almost every single sensor on their website that they sell. It tells you about it, tells you the theory behind it, how it works, what every component is, what every power line is, and all that stuff, so you can learn while you do it, how to test it, how to wire it, what you're doing with the wires, what it actually does, how to program it, step by step by step, all the way until it's working. Almost every single thing on their website, and quite a few others, SparkFun and Seed, and a lot of these different companies do this kind of thing to help you get started. If you want to get real crazy, there's a guide to programming in Python. You can get some very complex functionality out of these things. And the community, you're looking at millions of conversations here about people who just started out doing this, not knowing what they're doing, or people who are trying to do very complicated things. If you wanted to integrate a Wi-Fi card into it and run a server that pulls data down from your Arduino that's managing your tank environment and plot that, push it to a website, display it, all kinds of complicated stuff, and there's more than enough people to help you. This is just a quick little example of something that I used for a while. I had probably 13 different sensors operating on the tank, and it got real messy, so you can just real easily cook up some little thing in your head, and I switched to using Ethernet Cat5 cable. So all I have to do for all these temperature humidity sensor bundles is unplug and plug in a little Cat5 cable, and it runs all of the system. It's all self-contained and clean. You get real creative with all this stuff. Here's some basic code examples. I know it's fairly meaningless unless you're familiar with it, but I just want to emphasize how quick it is to get basic functionality, to learn how to code this stuff very simply, and then grow from there. And so like on the example on the right, you can see this is a little section that does the math to turn the temperature sensor reading into an actual temperature reading. I didn't come up with that. You don't have to have a math degree to do this. You can just copy it off a forum or a website, and it tends to work. Double check it. But this is real basic. It has a temp controller relay, some notification, LEDs, and that's it. And a temperature readout on the system running it. And this is for a very simple small tank. And then on the left, we have a more complicated one. This has two combined temperature humidity sensors, which this DHT.H means that I was able to import a library that took care of most of the complicated coding for me, and you just get to work with the fun parts, the parts that actually do stuff. We've got two switches, 4 temperature sensors, 2 more up here with the humidity sensors, some more math magic happening right here. But, say the readings were too volatile. I believe in this, I decided that the temperature readings fluctuated too much to be really meaningful, so I crammed them into an array of samples that it takes, and then it averages them out and decides which ones are important. One of the things that, say you have a very large tank and you want some kind of complicated control, like my tank, for example, it has 3 55-gallon sections with substrate in it. Most of the crabs tend to molt in 2 of those sections and just kind of play around and eat in the 3rd section. Well, I care about the substrate temperature of those 2 tanks that they tend to molt in more than I do about the 3rd one where they just kind of play around in. So instead of just having a basic on-off style thermostat, I actually weight the values of the molting tanks over the values of the other tank because I care more about it. It's more important. So if there's a temperature fluctuation in the playing around tank, maybe it doesn't turn the heater on until it gets worse, until it gets more off its target temperature point, because the other 2, where there's more crabs in them, are at the correct temperature. We can also split this into multiple heating zones where, different areas of the tank might behave differently. They might lose, if you have a bunch of pools on one side, you might lose a lot more temperature out of that side. So maybe you split it into 2 heating zones with multiple sensors and multiple relays and heat pads. You can heat the tank dynamically. The toppers above my tank, I keep them at a different temperature. I don't heat them. I don't value their temperature input as much as I do the substrate level tanks, because it's just environmental air. It's not as important, and it's going to fluctuate more often. This is an old little example of using some software, OBS, and the data output from the Arduino, combining multiple webcams. If you want to be able to be at work or wherever you want your kid to always be able to look at this stuff, you can stick webcams in there, use OBS to combine them together with each other and with the output, the data output from your tank sensors and the heating state. In this case, I have a cooling fan on this one, but you can chop that all together and output that as a live stream that you can look at whenever you want. I'll give another example for some kind of complicated behavior that I don't recommend. I'm just saying it. But let's say you have sections of your tank you want to heat and other ones that are always too hot, or you always have condensation building in your 3rd vertical topper because it's so far away from the heat source and you don't want to drive heat into it. So maybe you want to put exhaust in there. Well, you can also introduce humidity replacement mechanisms. You can use sensors to mix that humidity into the air so it doesn't soak one area of the tank. You can have it balance that humidity with addition and removal and, blowing air currents around the tank and manipulating the heat. And you can data log all this stuff and determine what the best, how to best reach a stable state in the system. Or maybe you want to introduce a little bit of variability, within the range of safety. Maybe you want to simulate some kind of weather in the tank or have a little bit of fluctuation so it's a little bit more like their natural environment without going too wildly outside of the ideal target zones. Or like the simulated weather, you can tie that into actual environmental conditions and maybe drop it a degree or 2 and you cycle through with some extra fans for wind, not necessarily from outside, just inside, so the humidity doesn't get impacted. But I really can't communicate well enough how limitless your options are once you get involved with using one of these homebrew Arduino or other testbed controllers and sensor packages. And if you happen to get really into this and really start learning the electronics behind it and the engineering involved, you can really do some amazingly complicated things with it and impressive things, not just for us in this community, but outside that community as well. There's people that work in zoos whose whole job revolves around this kind of automation and removing the requirement that a person has to be involved in every single thing that happens, or even if you don't trust relinquishing control of the systems to a computer or to software you wrote, you can at least put notifications, lights and sounds, alarms. If you want, you can attach a cellular radio to the Arduino system and have it send you a text message or tweet you when your humidity drops to a dangerous level or something like that. Or, you put one of those micro switches on the door. Maybe you get a text message when your cat tries to open your tank. It really is endless what you can do with this. And not really expensive. It does get expensive when you get into these complicated sensors. Some of those are very expensive. But, as with the hybrid controllers and the basic Arduino systems, if you don't have any electronics tools, maybe it costs you $100 to get into this, everything considered. But once you have, the soldering iron, the solder, and all the basic, the wire loom or heat shrink, and your basic set of tools to get in, which, by the way, they do sell kits if you don't know what to buy, is $30 a project. After you build your first project or two, it's free, because you already have all the components laying around. You really are only limited by how much effort you want to put into it and how much time you have to mess with it. And that's about it. I hope I've convinced at least one of you to get an Arduino or a discrete component thermostat and build your own system for this. Thank you for watching.